And I'm still paying you. I got them hard ass beats like the crack of the tech. Still paying dues. Think y'all forgot what rap sounded like? I'm still paying dues. Back to match up beats, the bang of the average. Still paying dues. I'ma make y'all pay for the dues.
This is databases. Introduction to databases 15.45, 6.45. All right, before we get started, again, apologize for running late, waiting for us, whatever time, and we had everything set up, and things were working at the last moment, so I apologize. Some quick shout-outs to people who help us get to where we are today. If it was a Greek out in California, JL in Seattle, my main man, Easy E in Crooklyn, and then I also want to recognize the people that aren't with us anymore. So it's been a year since DJ Drop Tables passed away, so RIP to him. And then DJ Mushu is still in lockdown in Cook County. We hope to get him out this year. DJ 2PL is still in Pittsburgh. I think he still dates the same girl as before, so he's doing fine. But the good news is that we have a DJ again, so give it up for DJ Cash. So it's worth pointing out DJ Cash is not just a DJ, he's also a producer, right?
Right.
So show us a little bit something what we can do. Go for it. The best part about this is like all those samples we can clear, whereas before we can always play everything we wanted on the internet. How you doing, man?
I'm doing great. How are you?
Wow. I was died last semester, so that sucked. But I'm not dead. I'm here. Everything's okay with you?
It would be nice if I had a lot more cash with me.
What?
I'm just looking for that money, man. Just here to get that money.
Okay, that's a weird thing to say. Okay. We'll take care of it. We'll be fine. Okay. We'll figure something. You should have told me this before. That's weird. All right. Sorry. All right. So today's lecture, we're going to go quickly through the some course logistics, and then we'll go jump right into all the course material. Again, so if you're not enrolled in the class, you're currently on the wait list. I think when I checked this morning, I think we're like 128 or something like that. I think the total enrollment is 130 or 140, something like that. So we don't control the wait list anymore because in the previous years we've had too many students trying to get on, and the wait list got too long. So the admins in SCS control this. So they will add people off the wait list as spots become available. So I can't promise you whether if you're on the wait list, whether you can still get in. And this is not official, but it doesn't go by your position for reasons I can't get into, but there's a lot of backroom politics between different programs, and it doesn't always go by the your position, okay? So the good news is that if you can't make it this semester, then it's offered every semester. So if you can't get this year, it'll be in the spring. If you want to make sure that if you do get off the wait list, that you're caught up to speed, Project Zero, which I'll talk about in a second, you should make sure you do that and follow along the lectures, because that Project Zero will be the determination whether you're allowed to take your class or not as well, even if you are bored. All right, so this class will be about the design and implementation of database management systems. How do you actually build this software, but what's going on the inside. So it's not a course about how to use or administer a database system. So some people say, like, why do I need to worry about building a system? I just want to use Oracle or just use my single Postgres, whatever. That's not this class. That's taught over in Heinz College in Information Systems. And this is really about the computer science level, understanding what's going on inside of the software to understand what these systems are actually trying to do for you. So again, if that's what you want, go over there. The camera's all what's going on there? All right. All the course logistics, the syllabus and the schedule are now posted online. So please go read that. Make sure you understand what's expected of you as a student in this class. All the discussion and announcements of the course will be through Piazza. If you're enrolled, everyone should have been added. As of a couple of days ago, I think I had to refresh it for the new students. And the same thing, grade scope, that'll sync with Canvas, so everything will be, the roster there will be added, or you can enroll there. And then final grades and the total grades throughout the semester, that'll be done through Canvas as well. And so we say this every year. If you're not in CMU and you really want to be taking the class, because we post everything online, You can go, there's a non-CMU student grade scope, use that code, make sure you put your university as Carnegie Mellon University, and then you can follow along and get all the things we have in the class. Except for obviously posting Piazza. So if you're not a student in the class, please don't email the students or the TAs or myself. Don't post your solutions on GitHub. If you are enrolled in the class, you don't want to be in this grade scope, you should be automatically added to the real one, okay? All right, so for in the lectures today, or throughout the rest of the semester, I get very excited when I talk about databases because I love databases. They're the best thing in the world. Number two in my life. I'll talk about number one in a second. But when I get excited, I start talking very fast, and then that can be hard for international students. So if I'm going too fast and you need me to slow down, just raise your hand and tell me, like, I don't understand that, can you repeat yourself or slow down, okay? And if you have any questions for anything that goes on in the lectures, again, please interrupt. Raise your hand and say, I don't understand what you're talking about on that slide as we're going along, and I'll stop and repeat myself. Because if you have questions, then it's very likely that somebody else is going to have questions too. So please go ahead and interrupt me. So what I won't do is that at the end of each class, I won't allow you to come up and say, hey, on slide 1, 2, 3, you said this, or what does that actually mean? So immediately after the lecture, you can't ask me questions about that lecture, because I want you to interrupt me as we're going along. Okay? So you can ask me about anything else after the end of the class, like how to get a job in databases, how to deal with the cops, or whatever you want. Like, that we can do, but I won't answer questions about the lecture. Okay? Because again, if you have questions, other people do, I don't want this to be sort of a back and forth collaborative. All the projects in the semester will be on this educational data system we've been building for several years now at Carnegie Mellon called BusHub. It's in C++ 20. You can probably get by with C++ 17 if you're not familiar with the newer features of the 20. But the main thing is going to be in C++. And there is no class at CMU that teaches you C++, so you kind of have to pick it up on your own. And so if you don't know C++ and you think you're going to learn it as we go along, that's probably going to be a bad idea, especially when it comes to debugging the system. Because you think about it, you're trying to learn C++ and trying to learn databases. It can be challenging to do this at the same time. So every year, every student comes along, or there's always students saying, hey, I know C++, and I know C, I know Java, I can pick up C++, and that's not always the case. So we have this assignment at the beginning of the semester that we outputted today. I had to fix up some things in the latest version of Clang last night, but it should be out in a few hours. Called Project Zero. It's basically implementing a simple data structure that has to be multi-threaded, and you don't get any grade for it, which is not meant to take a long time, but it's meant for you to come to realization whether you actually know C++ enough to get by in the class. So you have 2 weeks to complete it. You have to finish it, get a complete 100% in that 2 weeks, or you'll be asked to drop the course. Because again, when we start doing more complicated things like multi-threaded data structures, C++ is going to be very challenging for you if you don't have the experience. Okay? This also forces you to get a sense of your dev environment, all that good stuff as well. So any questions about Project Zero? We'll post information about this on Piazza, and the code will go out later today. And again, we try to get people to get through this sooner rather than later before we get past the add-drop deadline. So now, I have to show this every time in the class, warning about plagiarism, right? So everything you do for homework and the project should be your own work. Means we don't want you to copy from other people on the internet or other people in the class. But I'm going to say you are allowed to use generative AI tools, Claude, ChatGPT, pick your favorite one, to help you write the projects. Right? Because this is the future. Like, it's stupid to say don't use these tools. It'd be asking you like not use debugger to debug your code. It's stupid. Like, this is the way the world is now. So the lines get blurred. What's actually plagiarism versus not plagiarism when using LLM. And if you're not sure, ask us and use your best judgment. But by all means, you should be using these tools to help you write code. The tricky thing is going to be you can have that. ChatGPT will generate a bunch of code for you. But if you don't understand the fundamentals of what we're trying to teach in this semester and understand systems, you're screwed because you don't know whether the thing it's going to put out is going to be correct or not. And we'll talk about the leaderboard in once we release Project 1, but there's ways to get extra credit and based on how fast your code can actually run. And I'll be honest, I played ChatGPT and Claude and other ones, and sometimes it's correct, but it's definitely not going to be performant versus handwritten stuff. It's like writing assembly versus writing the C code in the compiler line. Sort of this thing might be. Okay? The other thing we're doing this semester is that we have, on every Wednesday, we'll have in-class lectures over Zoom from all our friends in the database industry. So we'll have these little flash mini lectures that'll cover quickly some particular database system or project that's out in the real world to get you to understand what, how the things we're talking about during the semester relate to real systems. We're also having all these companies come give recruiting talks in 2 weeks or 3 weeks in September. Everyone in the class will be invited to come to these things, and we can talk to them about internships and full-time positions as well. That'll be on September 15th and 16th. We kind of restricted this just to be the database classes this semester and maybe previous semesters, and then also the advanced class teaching being taught at the same time. Right, so it's not like the career fair with everyone showing up. They took a shower that morning, they're trying to hand you their resume. This is specifically just for databases. And we'll post on kiosk about how to do this. And then we've also asked the companies to provide us with information about their internship and full-time positions directly for CMU databases in the class. And that'll be on kiosk. All right, if you want to go beyond the things we're talking about in the class, we're also having a seminar series starting in September. This is optional for students. Every semester we always try to do a different topic. This semester will be about data lake systems. You know what that is, don't worry about it. We'll cover it later on. But this is sort of the hot trend right now where people are building cloud-based systems where they do SQL on top of files in Amazon S3 or cloud storage and so forth. So Iceberg is probably the most famous one of all these. Anyone knows who bought Iceberg recently or last year? Databricks. Everyone knows what Databricks paid for them? I think it was $2 billion or $1 billion with B. So we're talking about a shitload of money here. A bunch of these companies will come talk about what they're building. And again, this will be on Mondays after class at 4:30, and it'll be on Zoom and YouTube as well. Right? And this is option for students. If you're like me, you really love databases, you'll spend more time, and this is one way to do that.
Is there a reason why we don't have Databricks on these slides?
Question is the reason why we don't have Databricks in the slide? We do, twice. I've already said one. They bought Iceberg, they bought Tabular. There's one more in there from Databricks. Anybody know what it is? Delta Lake, yes. Absolutely, yes. So Delta Lake was Databricks' version of Iceberg, and then they bought the Iceberg guys. The story is the Snowflake was trying to buy the Iceberg guys. I think they offered them $600 million, and then Databricks swooped in and offered them like $2 billion or something crazy. Maybe it might have been $1 billion, it might be off, but still a lot of money. And then Snowflake put out Polaris, which is the catalog version. It's Iceberg compatible. Hootie came out of Uber, I think, and so Iceberg came out of Netflix. Uber came out of Hootie came out of Uber, and then now it's being commercialized by a company called OneHouse. You'll see it throughout the semester. There's a lot of different data systems out there because there's a lot of money in this. And every year, everyone's trying to build a new system to try to solve some problem that existing systems don't solve. And sometimes it's a good idea, and oftentimes it's a bad idea. And what this class is going to teach you is how to smell out which one's the bad ideas. And not just because I said so, because you understand the fundamentals of what these systems are actually trying to do. Okay? All right. Now, this doesn't relate to the class, but this is something because we're going to put this on YouTube. I sort of mentioned before that DJ Mushu is in jail in Illinois. There's actually somebody else we know who's actually in jail right now in prison. There's this guy named Preston Thorpe. So if you read TechCrunch or Hacker News, you might have seen this a few weeks ago, right? And he's got a blog article on Torso's website about how he's currently in jail right now. He got caught dealing pink or smuggling pink in from up in New England. So if you really read this blog article, he's got this little blurb in here. It says that while he was in jail, he started watching these classes, and he fell in love with databases. And he actually is currently in prison right now. We are trying to find a lawyer to get him out. And he's doing databases, right? So that's awesome, right? So I realize that there's other people maybe in the same boat. Again, everyone's here, and hopefully you don't end up in prison. But it's not just real. So this semester starting, if you're currently in prison, or you know somebody that's in prison, you send us an email and we'll send you a packaged up version of this course. It'll be like, if you don't have a computer, we'll send out some things, but like you'll be able to send you like a thumb drive, the videos, So obviously we can't send you this semester because this semester hasn't happened yet, so it'll be like in the previous semester, okay? And we thank our friends at Convex, which is a database company, for sponsoring us, okay? All right, any questions about the logistics of the course, what's expected from you? Again, the course syllabus will tell you the breakdown for the grades, for the projects, all the assignment lists, when all the projects will be released and how much released and when they're actually going to be due. And then you post all the questions on the author. Okay? All right, let's jump into this. So, as I said before, I love databases, but they're the second most important thing in my life. Number one is my wife and my biological daughter. Number two is databases. Like everything else doesn't matter. And you'll see this throughout your life that pretty much everything is going to be not just computer science and tech. Everything can be thought of as a database problem, right? So I don't have any friends outside databases. I don't talk to my family because they're Trump supporters. Like they don't like databases. It's just obsessively about databases. So what I'm going to hopefully impart from you in today's class and throughout the rest of the semester is how awesome databases are and why they're so important and why, again, you should pursue what I would call a database-centric lifestyle, which is every day you wake up thinking, how can I work with databases or how can I use a database? So in today's class, we're talking about data systems background. And I'll make a distinction between database and database systems, because they're equally important. And then I'll talk about the relational model, which is the best data model you could have for a database system. We'll talk about relational algebra, which is how you're going to actually end up write queries, so the fundamentals of building blocks of how you write queries and manipulate databases. And then I'll finish up talking about some alternative data models that are out there you may come across in the real world, and why they are inferior or just subsets of what the relational data model can do. Okay? And as I said, I love data so much I get really excited, so please tell me to stop and slow down if you have questions. Okay? All right, let's try to start with an easy question. Can anyone name a database? Just shout it out. Is it Postgres? One. What's that? SQL? Like SQL Server? SQLite, MySQL? Yes? You said SQLite, that's fine, right? For MySQL? ClickHouse, yes. One more?
Microsoft Access.
I heard Microsoft SQL Server. There's actually two products called SQL. There's super-based SQL Server and then Microsoft SQL Server. It's different things. Yes, right there, last one. MySQL, or MySQL. Redis, MongoDB. Redis is a bad system, we'll cover that later. You're all wrong. So what did they just all list? Database systems. I asked for a database. So again, because the course about databases, we can be very pedantic about what our definitions are, because we have to understand what we talk about when we say what's a database and a database system. Because we have to build database systems to manage it. So you're not wrong if you go to a bar anywhere and you're tech people and say, hey, I'm using this database. They'll know what you mean, but I understand what the data we actually want to store and what the systems we're going to build to actually manage it, right? So a database is going to be a sort of a collection of data that's interrelated in some way that's meant to model what the real world is. So we listed ClickHouse, Postgres, MySQL, SQLite. Again, these are all database systems that can be used to host and store and query a database. A database would be like the list of students that are enrolled in this class. You have a name, you have an email address, right? You have a date of birth and so forth. And what is that trying to do? I mean, trying to represent you guys that are taking this class in the sort of digital world inside of a database, right? And as I said before, these can be the most important computer application that you'll see for the rest of your life. Even if you don't take this class and go off and actually build database systems at all these various companies that we just mentioned, I guarantee you for the rest of your life you're going to come across databases and database systems. And what this class can hopefully teach you is like when you send a query to your database system and it's slow or there's something weird and it doesn't behave the way you want it to behave, this class will help you understand why that's the case. At the end of the day, what is computer science? Computer science is just like taking some inputs, doing some kind of manipulation on it, and then producing some output. That's a database at a high level. What is a file system? File system is a database. What is an LLM? It's basically like a database. Everything's going to be a database, right? Compilers, I mean, it's kind of rules inside of that thing, but it's taking some input, producing output. You could argue a compiler is a database. A game's a database. Everything's a database. Trust me. Okay. So let's look at like a simple example, and we'll see one way to get actually implement a data system to actually to maintain it and run it, and then we'll see why sort of this sort of Strawman idea is a bad idea, and once again, we'll help motivate why they actually build something more sophisticated, and why we need to do this course. So let's say we're going to build a clone of Spotify or iTunes, and we want a database to keep track of a bunch of albums that are out there, music albums, and then the artists that are on them, right? So what basic things we need to track is like the name of the artist, maybe the year that the album was released, right? And then what artists appear in different albums. When you think about what are we trying to model? The data is trying to model like a real music store, where you actually go in and see records and CDs and tapes and things like that. But here we're trying to do it inside of a database, so we're trying to keep track of all the attributes we have for those real world entities inside of our database. So what's one really easy way we could do this? Yeah, go ahead, yes.
Put the arm row of the album.
He said, put an artist name in each row. Yes, basically, but I'll be more specific and say, let's just say we have a bunch of CSV files, comma separated value files, or text files, that you have on your laptop or your computer. And I have one file for the artist, and one file for the albums. And as they said, I'll just have every line is going to be a different artist. Every line in that file, separated by a new line character, is going to be an album. And then I'll also have commas separate what they are. So I have one file for artist and one file for album, right? So now anytime I want to query this database, this is a database, now I'm just going to write some code to open up the file, call fopen, and then parse each line by the new line, split by the new line, and then split it by the comma, and find the data I'm looking for, right? So let's say that I want to write a query that says, give me the year that Jizza went solo, right? So I have this artist file, and I can write some pseudo Java code or JavaScript code that just opens the file, reads line by line, parses each line, and then I know that the first offset is going to be the name of the artist, so Jizza. So if the first offset, when I split them on the comma, is Jizza, then I know I have the match, and I just output the second line, record offset 1. You notice here, in the CSV file, everything's treated as a string. If I want to produce the actual integer of the year they went solo, I cast it to an integer. So, this is a good idea or a bad idea? I've already said it's a bad idea. So maybe why is it a bad idea? Yes? You said it's a linear time every time you look at one entry. Yes?
We never know when the next new line is, so we have to pass the entire file to each one.
They said in order to find any line, you got to parse the previous line to get to a sort of related. He said it's a linear scan or sequential scan to the file. Yes?
There's no typing.
There's no typing. Yes?
The logic and variable both field names are hard-coded.
They said
this is first.
he said the logic and the name or the offsets of the fields are hard-coded in the code. Yes? One more, yes?
No consistency guarantees.
Said no consistency guarantees. What do you mean by that?
Like acid, or like basically these people on the platform kind of like one kind of same model to really like.
He said no acid. Give us like 10 weeks before we get to that. Maybe another way to say it is like, there's no guarantees that the data I put in is going to be correct, and no guarantees that when I write the data that it's going to be safe, and no guarantees that the data across the two different files will be consistent, meaning like I could put an album that has an artist that doesn't exist in the artist file. That's basically ACID. We'll cover that later. All right, so we've kind of hit the major ones, right? So you can sort of think of it like in different levels, like the integrity of the data, meaning like if I put data in, because I'm trying to model the real world, can I manipulate and change the data in such a way that I can put it into an invalid state that doesn't match what the real world looks like, right? So as I said before, how do we make sure that if I add an album, I put an artist name, that artist name actually appears and is correct in the artist file? Or what if I have an artist that has multiple albums, the Wu-Tang Clan puts out a bunch of albums, how do I make sure that the artist name isn't like, I don't, sometimes use a hyphen, don't use the hyphen, so I have two different versions of the Wu-Tang Clan, even though logically I do the same thing, but the actual bits I'm storing are actually going to be different. So I'm going to think that they're not going to match. My sort of simple example here I was assuming that there's a one-to-one correspondence between an artist and an album. And an album would only have one artist, because there's only one field for it. People put out mixtapes all the time, or with collaborators. You have multiple artists on an album, but I can't represent that in that database. Then what happens again if I delete an artist, but I don't delete the album that they're involved in? Okay, now I have basically a dangling pointer. The implementation is going to suck as well, right? How do I find a record? As we already said, I got to parse through every single line and then jump to the offset, hard-coded in my program to find the data that I'm looking for. That's going to suck. But then what if I want to write a new application that wants to use the same database? If this one's in Python, maybe I want to write the next one in C++ or Rust. Right? I got to rewrite all the same logic I had before to parse these files now in a new program, and how to make sure that these things are in sync. It'd be really hard to do because they're different languages. And then what happens now if I have two threads trying to open up the file and try to write a new record at the same time? What would happen? Who would win, right? Is it the last writer wins, or should the second guy fail? Right? That's sort of related to the ACID stuff we just talked about. We'll cover that later. Then the last one is super important, because people get really pissed off if you lose data. Like think of your bank account. If you put money in, deposit money in the bank, and they lost that deposit, you'd be pissed, right? Because it's your money. So the bank does a bunch of stuff in their database to make sure that they don't lose those records. So, in our for example, it's not the end of the world if we miss an album, but people would get pissed off pretty quickly if the application didn't work as expected. Right? So what happens if we start appending new records to the file and then we crash? The computer crashes, some trips of the power cord. What should happen? What should you see when you come back? What happens if you want to duplicate the data so that instead of having on one machine and that one machine goes down and we lose everything, if we want to running a real website, a real service, it's got to be always available. So I want to start duplicating the data. And how to make sure those things are in sync. And so this is basically why you don't want to write a database system yourself in your application code. People do it all the time. It's a terrible idea. You want to use a database management system because this is highly vetted software that is where people are spending a lot of time not worrying about the high level things like how do I actually store represent a music site, but actually how do I store data and make sure you don't lose anything, right? So database systems are going to be important pieces of software that are going to be the bedrock for pretty much every application that exists today. Now, with that said, just because you're using data system doesn't mean the people building that data system have done that correctly and can guarantee that you're not going to lose any data or have other problems. This blog article actually came out 2 days ago. So there's a company out of the UK called SurrealDB, and without going into details, basically they turned off safe writes by default. It makes themselves look like fast, but get faster than they actually really are. So they're storing data very fast for you, but it's not actually safely being stored. So you can crash or lose power or something happen, and you can corrupt your database and lose data. So I'm pointing this one out because this was 2 days ago. MongoDB had a long history, we'll cover throughout the semester, where they were kind of pulling the same kind of games. Like this is not a new trend, this is not just pointing these guys out. I'm just pointing out to say that, again, what this class will do is teach you why what they're doing is a bad idea. And you should really understand what you're doing is claiming, what they're trying to claim that they can provide, and see whether it's actually real or not. This is something where they're hiding something in the documentation that nobody realized they didn't turn on until it was too late. All right, so now make the distinction between the database systems that we mentioned at the beginning versus the database. A database management system is this category of software that is meant to be for storing application data in such a way that it makes it easy to safely store data and to analyze it and ask questions about that data at some later point. So a general purpose database system, like the various systems we all mentioned today, like ClickHouse, MySQL, Postgres, Mongo, and so forth, right? These are designed such that any application that comes along could start storing their data in it without having to rewrite everything from scratch. Right? You can define the schemas, we'll cover in a second. You can tell the data what you want your data to actually look like, according to some data model, which we need the next slide. And then these systems will actually store this for you. As I said, this is not something you want to build yourself. Almost always the case. You almost never want to build this yourself. Oftentimes people say like, oh, there was no data system that met my needs, I had to start building my own. 99% of the time, that's actually not true. Right? You can get very, very far starting with Postgres or even something like SQLite. And that should usually be the first choice for building any new application. Actually, if you get nothing out of this course, remember your first choice should be Postgres. They have amazing front end, terrible back end. I'll explain why throughout this class. Okay? All right, so a data management system is going to provide you with, expose you what's called a data model, which is the high-level abstraction that sort of specifies how you're going to represent data in the database. Right? So a relational model is one example of a data model. The document data model in MongoDB, that's another example. We'll cover that in a second. Now you can think of these as like the rules that can define what types of things can exist and their relationships between each other in a database. Outside of like computer science, you can think of like a data model is like the rules for architecture. Like if you're going to build a building, right? A building would have things like a room and a doors. Like these are the types of things you're allowed to have in an architectural diagram or specification for a building. And then a schema is going to be a description of a particular database or a collection of data according to some data model. It's just like a way to define, here's the things that I actually want to store in my database according to the data model that I'm required to specify things as. So going back to my building example, you can think of the schema would be an actual blueprint diagram of a building, right? Say, here's where the doors are, here's the size and dimensions of the room, right? And I can take that schema and I can make different versions or different instances of that house or whatever that building is according to that blueprint. But the data model defines what the blueprint is allowed to have. Like it has windows and so forth, right? So the relational model is one example of a data model. It wasn't the first one. We'll cover the Strawman ones in a second. But pretty much today, most data systems are going to follow the relational data model. So pretty much all the systems everyone mentioned, except for Redis and Mongo, are relational database systems. For simple things, the key value systems, think of like, it's the most simple data that you can have, database you can have. You have a key followed by a value. It's like an associative array, like a hash map. You can jot in the programming languages, a key value pair. It's pretty basic. So you see this in like a lot of caching systems. Key followed by something like a blob or a chunk of data you kind of cache. Right, for simple things, it looks like this. There's a whole other category of systems called NoSQL systems. Raise your hand if you've heard the term NoSQL before. I'm actually getting less and less each year. This is good. I was not saying I was very prescient, but I was an early critic of NoSQL systems. And it turns out they're right, because pretty much all of them are adding a relational model now. But let's say there's a graph databases, they're not dead yet, they're still around. The document databases, JSON databases, XML databases, these are ones people mostly think about in the NoSQL world. Yes?
So is key value not NoSQL?
The question is key value not NoSQL? I mean, there is not an academic scientific definition of NoSQL. You could throw them in there as well, yes. This would be, like Redis would be a NoSQL system, that would be a key value system. But when most people think of NoSQL, they usually think of Mongo, Cassandra, things like that. Right. All these other data models we don't care about, except for the document itself, we'll cover in a second. Then there's array databases. These are like one-dimensional vectors, two-dimensional tensors, and matrices. You typically see this in machine learning workloads and scientific workloads. Except the vector stuff I'll talk about at the end. But this is very common now in relational databases. You use it to build RAG applications, do semantic search and near things. We'll talk about what that looks like. And then there's these guys at the bottom, hierarchical, network, semantic, and relationship. These are all the ones you see, really old systems from like the 1970s, 1980s. Hierarchical probably was the first one, network is another one that's around. Like you wouldn't, no new startup would say, I'm going to build my database or I'm going to build my application running off a hierarchical database system. Like that's like IBM IMS. They built that to keep track of all the parts of the Apollo moon mission in the 1960s. That thing is still around. IBM still makes a ton of money on it. Every bank still runs it. But they put a relational veneer on top of it. So it doesn't look like it did back in the day. So think of like 1960s, 1970s, early 1980s. We don't have to worry about these, except we'll see why they're a bad idea and then it'll help motivate why we want to do the relational data model. So this whole course is going to be a relational data model, because again, I pretty much in the same way that like 1 + 1 = 2 is the basic for arithmetic and math, the relational data model, in my opinion, is the basic building blocks of how you want to build any database application. The only time relational data models will make really sense is when you start doing matrices, because you can model them in a relational database. It's not always the best way to do that. Again, we'll cover these later on. All right, so let's go back to the 1960s. None of us were born yet. None of us were alive, but people were building database systems. Right, so in the early or mid-1960s, people started building some of the first database systems. The first one was actually built by General Electric, GE, in 1965. A system called IDM, Integrated Data Management. It's written in assembly. They built this to host some Seattle timber companies, their data applications. They keep track of all the logs or something like that. But IDS or IDM was the early ones. IMS, I mentioned, they built this for the Apollo Moon mission, before NASA it was actually called NASA. And so in these early systems, so before SQL for relational model, it was very hands-on about how you would actually write code to query the database. Like, I think people this even before C existed, people were writing assembly to do everything. And then COBOL came along, and it was still a higher level language, a higher level in assembly, but it was still pretty low level for how you'd actually interact with the database. And so there was this paper from 1973, I think, or 72, or 73, by Charles Bachman. He won the Turing Award for databases in 1973 because he built IBM and then IDS, and he had this thing called Codicil, and it was his way of how he thought how databases should look like. So the name of his paper is the Programmer as a Navigator. So he has this whole little step-by-step process here, is how someone would interact with, and could write queries against a database system. I don't care about the details of it. Just pointing out there's one, it's sexist, it can key everything. But two, also like he can do this, he can do that. The paper talks about you as a programmer being like Copernicus, or like sailing the seas as you navigating through your database to find all the data that you want, right? It's a terrible idea because it's essentially you as the programmer have to understand exactly how the data is being stored in the system and write code against those data structures. So it's got this little blurb here talking about some BS like the synergistic usage of the collection of which gives the programmer a great and expanded powers to come and go within a large database while accessing only those records of interest. This sounds like a terrible idea. But why? Right? Well, so again, this guy was a big proponent of something called Codicil. Nobody here has ever heard of Codicil. Probably never heard of COBOL. But this is how they were defining it in the early 1970s of what data should look like and how you program against them. So, what does it look like? Well, I've never written Codicil, but ChatGPT can. So, say we want to write a query that says, give me all the artists that appear on DJ Boucher's tribute album that we want to put out this year. Right? This is basically what it looks like. We're writing a bunch of nested for loops to look at all the artists, and for this artist, or all the albums of artists. Basically writing traversals in the data system of these explicit data structures to find the thing you want. You're essentially telling the data system exactly how you want to navigate the data to find the thing you're looking for. You think it's a good idea or a bad idea? I've already said it's a bad idea. Why?
It depends on which data structure you use in the underlying database.
They said it depends on what data structure you're using in the underlying system. There's one with the API wasn't exposed, but in this case here for Codicil, it's high level enough that they don't know what data structure is, but you need to know that there's data structures or collections you have to traverse. So in my example before, I had what? I had two tables or two files. I had artists and albums. Is it better to do the for loop on the artists first or the albums first? I don't know. Right? Well, maybe you do know because you go away and say how many lines or how many records are in each file. But that may be true today, but what about tomorrow or a year from now? And then, now this is the code you're writing queries on, and now maybe whatever assumptions you made at the beginning when you wrote this query is not the same as it is now. But because you've hard-coded exactly what execution plan you want, this computer has to run this. This is a bad idea. For a whole bunch of reasons we'll see in a second. But the equivalent SQL query would be something like this. Like joining the artist and album table by just the album ID. Right? And looking up on the album name. Notice here, it's if you've never seen SQL before, hopefully you have, I'm not telling you how to actually complete the answer I want. I'm just telling you what the answer I want. And then the data system, it's their responsibility to go figure out how to actually generate that answer for you. Right? It seems obvious now, but back then, this was like a mind-blowing idea, and codicil was considered the hot thing. So I don't know too much details of this, but there was this meeting of the minds in 1974 at University of Michigan in Ann Arbor, where all the codicil guys came along, they were there, and all the relational data model guys were there, and they thought about it, and it's all public, everything's written down what they were talking about. And they were pointing out all the reasons why a hierarchical or navigation data model is inferior to something like a relational data model. And this was considered a major pivotal point in databases where now people realize, oh, the relational data model is the right way to go forward. But at the time, there weren't really any systems that could actually implement this. And then after this point, people started building that. So the guy that proposed the relational data model is named Ted Codd. And so he was at this conference, along with the codicil guy I just mentioned, Charles Bachman, as well as Jim Gray, the guy who had 2 days locking and built one of the early systems at IBM called System R, we'll cover next class, as well as Mike Stonebraker, the guy who built Ingress, who then later built Postgres. You never wonder why Postgres is called Postgres, because it's post-Ingress. He built first Ingress, then he built Postgres. That's the follow-up, right? There have been 4 Turing Award databases. These are the 4 right here. First 3, Codd, Bachman, and Gray are all dead. Stonebraker's still kicking it. He's like 81. He's awesome, right? He's helping us trying to find a lawyer for the guy getting him out of jail. Right? But this was like a big conference, big deal back in 1974. And so the codicil guys were saying, oh, the relational model, because the paper came out in 1970s, early 1969, you couldn't build a system to do like this. It's way too complicated. Nobody can reason about relations in a database. And then the relational database guys are saying, all the crap they're talking about codicil, like navigating through your database, it's a terrible idea. It's going to make your database really brittle, and you're basically hard coding exactly what the query plans would be. And again, it's 30, 40 years, or 50 years later, and the relational data model guys have won because you all listed relational databases at the beginning. No one listed a codicil database. They still exist. You still can pay money to somebody to maintain it for you. But those startups are building new systems today. All right, so what is at the core of the relational data model? 3 basic key ideas that are really simple to understand. The first is that the way you define your data through the data model is just that these high-level collections of data are called relations. Basically, think of as sets. And that you would then represent the connection between data at the logical level through values. Say like this album is part of this artist is this album, by saying like keeping track of like identifiers between those 2 relations, rather than low-level physical pointers like this memory address or this disk offset to say that things are related. Everything is done at sort of a high-level logical level. You also can be able to specify constraints now in your data to say what data is allowed to be stored in it to make sure that nobody's allowed to put invalid data. Like in my file before, it gets just a file and disk. I could open a text editor and start changing years into email addresses. And that would break all my programs. A relational database will prevent you from doing that because it'll say this column or this attribute has to be this data type and doesn't let you store anything that would violate that. Now, always true, some systems will see like SQLite, which you store a bunch of crap in there you shouldn't have. But the relational data model is sort of separate from the implementation. And then the last one is the way you would manipulate or query the data is through a high-level API that you declare what answer you want, defined through relations. You can think of like set theory, basic sets. And then I don't care about the actual implementation of the database system. In my query, I say this is the answer I want. And now it's left up to the database system to decide the most efficient query plan, the most efficient way to store that data and execute that query for you. So any assumptions you made during the time you wrote that query, as the data changes over time, and the same query shows up, if I wrote it in SQL or whatever high-level language I want, then the database system will say, oh, my data actually looks like this before it looked like that. So here's actually the right way to run the query, instead of the faster way to run the query rather than before. Or here's the best way to store the data you're actually storing that you want right now, rather than what I thought it looked like before. So we have this nice independence between the physical level and the logical level, which I'll show you real quick in a second, that allows it a bunch of freedom to the data system implementation to do the most efficient way to store things. Question? All right, so let's talk about this independent thing. Again, so this is the 1970s. Computer science was still in the early days, so this is obvious to us now, but back then this was mind-blowing. Like in IMS that sits from IBM, they mentioned about the API. In IMS, you declared, I want to store this table, and it's either going to be a tree data structure or a hash table or hash map. And then depending on what those two data structures I chose, I got a different API. Because I can't do range scans on a hash map, and I can't do certain kind of lookups on the tree. But then if I decide, oh, that was a mistake, I actually want to store my tree structure in a hash structure, or the reverse, I got to go back and rewrite all the code to reflect that change because the API is changed. But in a relational data model, in SQL, or any high-level language like a relational data model, I don't have that problem because I don't know what the data structure is. I'm saying I want to access this data at the logical level of a relation or a table. Right, so at the lowest level, we have this thing called a database storage. And then above that, we would have the system keep track of like the physical schema. Like I have a bunch of files, a bunch of pages, I have a bunch of extents I declare on this storage medium. I'm keeping track of where all the information is and where the bits are stored and how they're being laid out. And then above that, I have the logical schemas that would define what my tables are, my collections are, what attributes they have, what their names are, what their data types are, right? And I have a nice separation between the two of them. So if I change one versus change the other, I can change one without necessarily maybe changing the other. I can change the physical layer without changing the logical layer. And go even crazier, I can have another level of the external schema. And this is a way to expose or abstract away further what the actual logical schema would be, so that maybe I can do certain things or have certain data exposed a certain way without actually changing the logical level or the physical level. So say I have a table of every student in this class. Maybe there's a column for like your password or something like that. But I don't expose that password column to every single application that they want to access that table. So I can declare a view to say this is what you're allowed to see and hide certain things. It's just another level of abstraction. And above that is what the application is going to see. You would access it through a high-level declared language, something like SQL. So you think of this point here in our graph, that's the physical data independence, because I can declare my schema, here's the columns that I want, but I'm not defining how I actually want to store them. And the data system is free to change this lower level all at once. And it doesn't break your application. And then logical data independence will be up here, because we won't cover this too much in the semester, but it's basically a way to say, yes, I have this schema, but for certain applications, they see certain things, and certain applications should see other things. And I can change those things without having to rewrite anything else above. All right, so I've been going on for the last 10 minutes about how great the relational data model is, what actually is it. So at its core, it's going to represent everything as relations. And just think of relations as like a set, an unordered set where we keep track of the relationship, not between the different collections. There's actually the relationship between the attributes within a single collection. Right? So you have a student has the name, a student has the email address. The relation represents those relationships between those attributes for that high-level entity as a student.
In the previous slide, what part of this hierarchy is a database management system handling?
The question is, what in this slide here, what part is the database system handling? Everything before the application. Everything. Right? We'll go throughout the semester, but like down here, big thing is like the operating system. Operating system is terrible. It's always getting in our way. We hate it. sorry, revisit that. We need it to survive, not always, but we need it like to do certain things for us, but we almost, as a data system, we always want to do things without the operating system. So you can think of like maybe the OS is kind of in here, but it's always going to be a big problem for us. We try to get around it. We'll cover that as well. But everything below the application down is the data system. Sometimes you can put the whole application in the data system too. Not always a good idea. And those people write code that way, but you could do that. It could be the whole thing. But for this semester, we'll say it's the application down. Other questions? All right. All right, so relation is going to be an unordered set of data. And then we'll say that a tuple, sometimes people call them tuples. This is around a couple, but I say tuple. A tuple is going to be the set of the attributes within a sort of a single entry within within a relation, right? And then for every attribute we have, there'll be something called a domain that specifies what the range or allowed types, allowed value instances is allowed to happen. So if I have an integer, like if it's 32 integer, the domain would specify from like 0 to 2 to 32 minus 1, or if it's unsigned, right? If it's a name, it'd be like a string field and so forth, right? It's basically defined what that's right. We'll have a special value of null that's going to represent, remember, every domain, if it's allowed, we have a string because they can't have null. But it's a way to represent that the data is unknown, right? And it'd be very similar to nulls in C code, but it's at the sort of the logical level where there is a value we're storing for null, but we can't reason about anything about it. So we can't ask questions about what that value actually is if it's null, because the answer is unknown. Does it make more sense next class? We'll see it, but the main thing is that you think of like a relation as a tuple or table with n columns. And most of the time people don't refer to them as relations, people refer to them as tables and columns and rows. But when we talk about different storage models, what a column is and a row is doesn't always line up exactly with this, but for now this is fine. And so in a relational model, we'll have what are known as primary keys. These are ways for us to uniquely identify a single tuple in a relation. I think it's like a unique value that uniquely identifies a single record. And you can define unique values in other columns, but it's not always considered like the identifier. Right? And that was going to the primary key. So in this case here, for our artist table, we have Wu-Tang Clan, we have Notorious B.I.G., we have GZA. But certainly there's bands that come along that have the same names as previous bands, right? Sometimes they try to be tricky and remove vowels and make sure the names don't match. But oftentimes it doesn't exist. So in this case here, using the name would not be a good primary key because two artists can have the same name, right? So oftentimes you see databases introduce sort of synthetic primary keys or identifying columns. Sometimes they're called identity columns. Think of like it's a unique number we assign to some record. Oftentimes when you see websites, you look at the URLs, it'll say when you see like a number represented with an order number, it's almost always going to be something like this. It's a counter going up for every single order that comes in.
You have a preference on what is your preferred form of using identification? Would you prefer natural key or new identifier?
This question is, what is my preference? Should we use a natural key or an identifier? We didn't find what a natural key is. A natural key would be like
for example, the name.
Yeah, the name would be like a natural key, but in this, it would be a better example here. At CMU, a natural key would be your email address, and that's again unique. Sometimes there's programming frameworks like ORMs. They'll automatically generate you these identity columns. I always just use them, right? So I think it's fine. Right. So in this case, the primary key now is the ID column, because we're going to say every time we insert a new record, just think if there's some counter called a sequence, we add one to it every single time we add a new record. So it's guaranteed to be unique. We can also have foreign keys, and this is how we're going to allow us to identify the relationship between different tuples within different collections or relations themselves. So going back here for artist and artist album, so artist and album, right? So now I've added the ID column that uniquely identifies each record as for its primary key. But now in the case of the album, I want to keep track of what artist appears on it. And for certain albums, this is fine if there's only one artist. Right? I could have a mapping between, I could basically store the artist ID within the album itself, and I know how to map that back up. But as I said, the challenge is going to be is when I have albums that have multiple artists on them. Like in this case here, the St. Ives mixtape. So to represent and model this, I can introduce new sort of cross-reference or dependency tables that allow us to be able to store the relationships between records or tuples across different collections or different relations. So in this case here, I would have a separate table now, keep track of the artist ID and album ID, and I have a record in this table anytime an artist appears on a given album. So this allows me now the freedom to represent, have multiple artists appear on multiple albums, and not assume there's a one-to-one correspondence. Basically, I can do many representations of this. And now I don't need to store the artist ID in the album itself. I just represent through that separate table. I'm going to skip constraints for the sake of time, and I apologize. Basically, it's a way to specify what values are allowed in additional constraints beyond just the data type. So I can say things like, name can be null, I put a not null there. I can have other constraints to say like, no artist can be born or can go solo before year 1900. It's a bad example. We can imagine other things like no email address at CMU cannot contain andrew.cmu.edu, right? Something like that. You can declare this when you find a table. You can also sort of have global assertions. Basically, every single time you insert a record, it runs a SQL query here to check to see whether that's valid or not. Most systems don't support this because it's slow, but it's a way of allowing to model more complex constraints and data restrictions than the basic one in the code tables. Yes. Question: what is the foreign key? Sorry. Thank you for stopping. So foreign key is going to be the foreign key in this table here would be over here. So you have a relation that's defining values, but you're saying that for a given column or attribute, it really is a value that has to exist in some other relation here. So I would say I'm declaring this relation, I call it artist album. I have an album ID and artist ID. For any album ID in this column here, that album ID has to exist in this column here, in this table. And that way I avoid the problem of like, if I delete a record here, then I don't want to have a dangling pointer where I have now an album that has an artist, I have an artist that's on an album that doesn't exist anymore. The database would know, okay, you're trying to delete an artist, but I know that I have a foreign key reference to the artist ID here, and this has a foreign key reference to an album over here, so that prevents me from deleting one and not the other. Yes?
What's the primary key of
The question is, what is the primary key for this table here, relation here? So anytime I have the underline, that's the primary key. So it's actually the combination of the two columns together is the primary key. Can you do it in SQL? Absolutely, yeah, why not? The question is, can I declare a primary key with multiple columns? Absolutely, yeah. Why not? Yeah. We can see that next class. Okay. So what I've talked about so far, again, is the high-level concepts of relational models, how to define a relation or a table, right? Again, the terms are used interchangeably. Like in SQL, you would say create table, right? You refer to things as tables, but in the sort of research literature or in the original definition of the paper of the relational data model, they weren't called tables, they were called relations. They're basically the same thing. So now we have to find what our relations look like. Now we want to actually run queries on that. So this is called the DML, the data manipulation language. But even though also too we're not going to be, we may have read-only queries like select statements, they still fall under the category of the DML because I'm manipulating the data to perform it somehow. So there's basically two ways to do this. There is a procedural language and a non-procedural language, or declarative language. So what I'm going to teach you today will be relational algebra, which will be a procedural language, where I'm defining the exact steps I want the data system to use to execute my query. And I'm actually defining the order in which I'm going to execute them, which actually goes against what I said before, where you don't want to be doing that. You want to have things be high level enough where the data system can decide the best way to execute that. And And this is what Ted Cod defined the relational model with the relational algebra at the very beginning. And then the high-level languages that allow you to do have that declarative interface, that came later on. The declarative way of using what's called relational calculus. Right? SQL basically maps to this, so we'll cover that next class. You don't really need to know relational calculus unless you put it into a query optimizer, which is not this class for the most part. We used to teach relational calculus in this class, but you go out in the real world, nobody uses it, so you don't really need to know it. But you already need to know relational algebra because that's going to be the fundamental building blocks of how we're actually build the implementations of systems, the execute queries. Okay? And again, it should be pretty straightforward to understand. All right, so relational algebra is the original definition from Ted Cod posed 7 operators listed here. I'll go through each one by one. We'll see at the end, this has been extended over the years for things you actually need in to run real queries. Like, there's no notion of sorting in these operators. There's no notion of doing aggregations. Like, think of like creating the average of a column. Like, that all came later as extensions, but the original ones are these 7 here. And you can think of like, you can build more complex queries from just these 7 operators by chaining them together, where you allow the output of one operator to be fed as the input to the next operator, and you can use that to build larger, more complex things. Right? Again, we'll go through each one by one, and I'll show you what the corresponding SQL looks like. And then that'll segue us into next class. All right. The most basic operator you can have is called a select statement. And this is just like you're filtering out the tuples you don't want based on some predicate. You're defining the first order predicate logic that say these are the tuples that are allowed to be emitted as the output for this select operator. So say we have a simple relation here, R, it has 2 attributes, AID and BID. So I can have a select operator that says, give me all the records from, or the tuples from R, where AID equals A2. Right? And then there's the data set is somehow filtering out that data according to that predicate and producing the output. I can do more complicated things. I can start combining them together through conjunctions and disjunctions. I can have multiple predicates be evaluated. So in this case here, I'm saying, give me all the tuples from R, where AID equals 2 and BID is greater than 102. And that produces the output. Again, in SQL, it's basically equivalent to the where clause. Right? And it's just Boolean logic to define what predicates, or sorry, what tuples to match according to the values of whatever I'm defining in my expressions. Right? And it's just a one-more correspondence. So that's pretty easy to understand, right? I can also have what's called a projection. A projection just allows me to manipulate with the output of those attributes that I'm selecting on in such a way that I need them, the way that I want them to produce it as part of my output. So I can rearrange the ordering of the attributes. Like I can put one column first before another one. I can remove columns I don't care about as part of my output. Remember I said filtering out things like the password of a table, because I don't want somebody else to be able to see that. I can do that through a projection. And I also manipulate the values of the attributes, derive new values according to whatever it is that I want for my application. So you define something like this. So this here I have my select operator where I'm filtering out all the records where AID equals 2, and then I define my projection that says take the BID attribute for any tuple that matches after my select that's being fed as the input, and take the BID attribute, subtract 100 from it, and then produce also the attribute AID. So again, in a select statement, projection is just sort of this front part here. After the select, you're defining the projection list. You're defining the attributes you want to come as the output. Yes?
So the previous slide was called select. Like the title of the previous slide was select.
Yes.
Really, we were talking about like the where keyword, right? The previous slide. So is the word select in SQL and in relational algebra different things?
It's the same is the select operator in relational algebra, is that different than the select operator in SQL? Think of like a select as the select operator in relational algebra is it's a way for you to think of these relational algebra as the building blocks to build a larger language like SQL. So So you need a where clause, and so the relational operator and the select relational operator will give you that where clause. You need projection out list, project operator will give you that. And then the from clause will be joins, whatever.
So, as a follow-up to that, if that operation, instead of pi, we said sigma, is that a valid operation?
The question is, instead of using pi, if I say sigma for select, with the reordering of the attributes,
The same, the
Which one?
BID minus 100, comma, AID.
would that work with a select operator?
If I replace the projection with a select operator sigma,
No.
is that valid?
No, it's not. This question is, if I instead of using a projection, if I do a select operator with the same expression, is that still valid? Well, in this case, no, because I have a comma separated list where I can't evaluate whether a tuple evaluates to true for that expression list. If I only had BID less than minus 100, what does it mean to evaluate that in Boolean logic? BID minus 100, it equals whatever that value is, but is that true? Technically, yes, because it's not 0 in base Boolean logic. So that would always evaluate true. But the semantics are not the same. You just can't swap them out. Yes?
So earlier you mentioned that the relational database is intended that clarify something, but then you said that this is procedural, so
Yes, yes.
I suppose SQL is supposed to be a declarative language, and then the relational algebra is procedural, but they basically look the same thing, so it's different.
Give me like 4 more slides, and then we'll come to that. The question is basically, I made a big deal about how you want to declare the language like SQL, but now I'm showing you like, defining the order of the steps based on relational algebra. Relational algebra will be the building blocks for how we can then build a declarative language and drop it out. Another way to think about this is like, when I build the execution engine for in a database system, the thing that actually runs the queries, it's going to look a lot like relational algebra, because I'm going to find a project operator. Yes.
That's like it combines like one big thing that it's like
The statement is, sorry, maybe another way. Are all these operators commutative? Not always, but sometimes, yes. Actually, it's actually true. Relational algebras are always, if you start projecting things that you haven't produced output yet, then they're not entirely commutative. But in general, yes, they are commutative. The point I'm trying to make is like when I build the execution engine to run a SQL query, it's going to, the operators, the actual implementation of the execution engine, it's going to look a lot like relational algebra. But we'll see the distinction in a second. But the point maybe to point out is like, if I took relational algebra as my input and actually started executing it, I would execute it exactly in the way that's defined in relational algebra, which is not what we want and have all the freedom we want, and that's what SQL does not going to do. SQL is not going to have that problem. Yes?
So this SQL that's on the screen, is that a select or a projection?
The question is, what is this select statement here? It's a it is a select statement in SQL that contains a projection clause. And you can think of like BID minus 100 is equivalent to the pi operator with this expression above that.
So that's not still that exists right now, that's being inherited from this projection.
So the question, the output here.
Yeah.
Is it correct? Any output of a SQL statement is going to be a table or relation. Any output of a relational operator in a relational output is going to be another relation. So you can daisy chain them together and take the output of one and produce that input for another. Okay. Union is pretty straightforward, and if you know basic set theory, which you should have, because that's a basic mathematics prerequisite in this class, you can union together two relations and concatenate all of that. It removes duplicates. So for this, in union operator, intersection, and difference, you have to have the same attributes in the two relations, because otherwise it doesn't match up. Because the output needs to be the output relation for the operator needs to have the exact number of the same relation, the same attributes as its inputs. You can do this in SQL, basically something like this, right? I'm going through this fast, I apologize. Intersection is basically the same thing, right? They have to have Both input relations have that same attributes. Same for difference. Again, this is all basic set theory. This should not be anything new. You can do the same thing in SQL. The reason I'm rushing is I want to get to joins and Cartesian product. So up until now, what have we done? We've taken one relation as our input, manipulated it, and taken it as the output, and sent it along to as the next operator we look up on. And then for union and intersection and difference, I'm combining together multiple relations, but I'm not really leveraging any of the relations between the values within those relations. I'm not leveraging the foreign key stuff that we talked about before. I'm running out of battery, so there we go. So with joins and the Cartesian product, the idea is that we can now combine them together and do some lookup to say what tools should actually satisfy when I combine these records together. So Cartesian product is just literally just mashing together the two attributes, the attributes of the two relations, producing a larger tuple that has all the attributes from one relation with all the attributes of the other relation, right? You can do this in SQL, you pass along the cross join, or you don't specify cross join, you get that by default, right? But this is not actually what we want, because we want to say things like, for a given album, give me all the artists that are on that album. You don't want to get all combinations of artists and albums. So that's kind of it's a bunch of noisy data that I don't care about. So this is where the join comes in. And you can think of a join as like a Cartesian product, where you have a filter to say, I have a select predicate, say these are the tuples that should match according to some value in one relation and the value in another relation. So I can do things like this. If I don't specify what the join calls in, it's called a natural join. And in this case here, it's going to take all the attributes that are in one relation, all the attributes in the other relation that have the same name, the same type, and I look for matches and I produce my output. Right? And I'm going to include all the columns that are in both the two relations as they would in the Cartesian product. Just I remove any of the duplicates here. So I only get the attributes that are unique from one column, from one relation and the other relation. So you can declare this as SQL through a natural join. I don't recommend doing that because it's implicitly doing a lookup between the different relations to see where the matching attributes are. You said you want to use a join clause where you can specify either what attributes you want to join on, or what I would recommend is explicitly saying what the join predicate should be, so it knows how to do that match. In this case, the question is this an inner join? Yes. We can cover outer joins later. All right, we're almost out of time, so I'm going to quickly say there's other operators that exist. I'll finish with these last two slides, and then that'll segue into the next class. But as they pointed out, the relation algebra I showed you so far, that's specifying the order in which I want things to apply. Right? So I want to say, give me all the join relation R, relation S, and do a lookup for a filter on the BI equals 1 or 2. I can have wildly different performance of these queries if I do the join on R and S first, then do the filter, versus do the filter on S first, and then do the join. Right? Always think of extremes. It's something I say throughout the entire semester. If I have think of a table with 5 records, think of a table with a trillion records. So do I want to do a join between R and S of 2 tables with a trillion records, and then filter out the ones I actually want? Because what if only 2 match? And I did a bunch of join, a bunch of tables I didn't actually need. And I'm better off maybe doing the filtering first, then do the join. So this is what the high-level language of something like the type of language like SQL is going to do for us. I'm going to say this is the answer that I want, and I'll let the data figure out the best way to actually get it. So I'll stop here and say this is where we're going to go next class. And now we're going to say, instead of writing procedural code, you do the Python procedural language or whatever, this algebra, we're going to be writing SQL. Okay? All right, hit it.
Cash money, flick, flips, acrobats over tracks. 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 Get the fortune, motherfucker fan.
Maintain but never strain, flow with the grain. Get the fortune, motherfuck the fame. Maintain but never strain, flow with the grain.